Hello everybody and welcome to Handmade Hero. We are going to be taking a look at the lighting code today because when I did my survey last week of stuff I wanted to improve, I was going to say like, oh, we should simplify the lighting because it's too complicated and it doesn't look good enough and whatever, because that was like my recollection of it. But actually when we looked at it, I realized the lighting actually seems to look quite good. Like looking at the lighting here, it actually looks quite nice, and I was like, maybe we're actually pretty close to having like high-end lighting that actually is pretty good. So I think maybe I spoke too soon. I think maybe we just keep this. But there are a couple things that I wanted to take a look at today, because I think there's some things we can do to improve it. So what you can see here is like the best case for the lighting. This is what happens if we effectively sort of ignore any high any high frequency updating to the lighting. You can see that it's quite laggy right now. Like you can see it takes a while for the lighting to come in. So this is a long-term average blend of the lighting, and you can see that it does look quite nice when you give it enough time, right? But it's too slow. And what I sort of looked at the other day is that if you actually look at the code and how the breakdown of performance looks in it, in fact, I think we can still sort of see that here if we go into the profile. So if we take a look at the actual like clocks here, I don't know to what extent I can actually look at these, but if we actually look at the way these clocks break down here, if I remember correctly, so you can see the lighting takes all the time. That's our pretty much only real expensive thing we do, because we're doing it on the CPU. We haven't moved it to the GPU, which we still might do someday. There's a lot of efficiency to be gained by moving it to the GPU, not necessarily because the GPU will do it all that much faster. It's really not so much that. It's more that because the GPU is the thing that's doing all of the pixel fill, the fact that we have to move the data from the CPU to the GPU every frame is kind of a waste of everyone's time. So, you know, there are some efficiency gains to be had here, but in general, that's taking all of the time. But if you look, you can kind of see that we're still like almost getting 16 frames a second, even just at the 60 frames a second. We're not quite hitting it reliably, but we're close. And this is with full 3D on the lighting, which we sort of decided we don't really need the 3D, and we're probably not going to stick with the 3D, which means that a couple things. One, if we eliminate the stacking that's going on here, right? If the stacking gets eliminated, then there's far fewer light probes to compute. Right now, I don't remember the exact Z-stack for lighting. I think there is some kind of a parameter here that we threw in there that actually I should probably go to the Handmade directory here first before opening up the editor. There is like a set of parameters here that are related to that. I don't actually, like I said, it's been a long time since we looked at this, so I don't actually remember exactly what they all are, but there are like basically like dimensions here for it. And you can kind of see that like there's some parameters here for tuning what the voxel dimensions are going to be for like the lighting. And in a lot of cases, we could just simplify this down quite a bit. And while we, I think, already cull out, we don't sample light probes that are just floating in space and that don't actually do anything. So we may not save a whole lot of processing time on the CPU side for that. We would be drastically reducing the footprint of the thing that we're producing. Because remember, we have to send this voxel down to the GPU every frame, and if we cut out 16 layers of that texture, then that's a dramatic savings, both in terms of like cache footprint on the CPU side. Because remember, right now we're also still using floats. We haven't converted to something smaller than floats, so these textures are quite large. So you can kind of get a feel for just how much savings we could get here. Similarly, right now, I think we're undercasting. We were able to optimize the Raycaster quite a bit, and while I don't remember the exact breakdown between how much time it's currently taking for us to basically do like, how much time is it going to take us to do raycasting, how much time is it going to take us to do blending of the texture maps. If I recall correctly, blending the texture maps was a major part of the time sink, which means we could now, because the raycaster is much faster, cast more rays per texture blend, which would get us much more high-frequency lighting at the same quality level, right? Well, not exactly the same quality level necessarily, although perhaps. It's hard to say. So I do think there's like a lot of things we could do here that we could use to sort of improve the state of our lighting system that don't really require us to do much hard work, right? Like we're not confronted with any real research problems for those things. It's literally just like, okay, cut out one dimension of the lighting so it's just flat plane. And it's still doing the lighting calculations in 3D, right? But it doesn't calculate stacks of light probes. It just calculates one sheet of light probes. It's huge savings for no visual quality elimination there, right? Almost nothing gets eliminated, and that so on, right? So all of that's good. And then similarly, we don't really have we don't have much limitation to casting more rays on every frame, I don't think. I think we could crank that number up a little bit, and it would probably be a pretty substantial improvement in the lighting for not a huge hit to the frame rate. So I think we probably want to do that. I want to see how hard it is to actually remove the Z sampling here, but I think that's like the first thing I want to do to just get rid of that so that we're just talking about one sheet. So the light lookup voxel dim Z just goes away, basically, right? So this is going to be a pretty major change. It's not difficult, but it's going to be a couple different steps of making the change. So I'm going to try and do it slowly. So what I'd like to do first is just see what happens if I change this to 1, right? If we just eliminate one of our light lookup voxel dim Z's here, and maybe I take a quick second, hot second as well, to just look for light lookup voxel dim Z to see how many places this is actually being used, because again, I don't really have a good feel for what that state of that code is right now because we haven't worked on it in a while. So you can see here where we initialize the dimensions of the voxel lookup system, right? And you can see us doing this make light atlas. We have the make light atlas function here. You can see the way this works is it basically takes any arbitrary voxel dimension that you want here and produces information that it can use to index into the voxel. Now, if all I do is change the dimension, in theory, if we wrote this code correctly, it should still all work. One problem that we're going to have is the lighting bounds are going to be a little bit trickier for us to compute now. I mean, in some ways, they're actually simpler for us to compute, but we have to go find where that's going to be. So when we make this light atlas, for example, you can kind of see that, well, when it makes the light atlas, it doesn't really think much about the actual, like you can see this light atlas tiles dim that gets passed in there. It's thinking more about just like the texture that has these tiles in it. It's not really thinking about where they correspond in the world. Right, that's not a thing that they actually are used to. This is in the profiler. I don't even know why we're looking in that code. Hold on a second. How do I get back to the search or the list? Can I do that? I don't know if I can. Let's list again. Light lookup voxel Z. Oops. Light lookup. There we go. So yeah, we do have that lighting profiler, which we built separately, which we could also do. But again, I really just mostly care about the lighting stuff in the actual code here. Let's go over here. You can see this is the OpenGL initialization of the light lookup voxel, right? You can see it here. You can see it making the light atlas and allocating the actual space that it needs for it and all that sort of stuff, right? And like I said, so in theory, we should be able to set this to 1, but we could also eliminate a lot of the code complexity here by removing that parameter entirely. So that's also something we would want to do. Now, in the actual world code, in world mode, where we're actually running the main game loop here, which is in here, this code here, if we take a look at the lighting calls, you can see here we do sort of a pass to gather, like stuff that's going to be in the lighting, right? And you can see down at the end, after everyone has done everything, we call update lighting here. And you can see us passing, like, you know, a bunch of primary values to this thing. So you can see, for example, us passing this world mode fundamental unit. Yeah, you can see us passing, like, the 2 atlases down. You can see us passing, like, where the lighting is going to occur, and so on. So in the update lighting call, you know, it's going to rely on, let's see, here we go. It's going to rely on what it gets as these particular values here to determine, like, the span of this voxel grid. And you can actually see the calculations of the lighting area right here. Every time that the general size of this thing changes or whatever happens, it recomputes, like, how the spatial grid is aligned and what the it's called a walk table that we made here. It's basically the thing that allows us to walk through nodes of the voxel for raycasting and things like that. And as far as I know, these are sort of aligned with the lighting grid. I don't remember us using 2 different spatial resolutions for those things, but I could be wrong, because there's no real reason they have to be equivalent, but I think we may have made them equivalent because of certain efficiencies we could gain from it, if I remember correctly. So then if you take a look at what happens here, after we, you know, ensure that this is built, because this only happens, like, once, right? This only happens if you change fundamental lighting parameters. So it's probably only going to happen once in a run of a game. At startup, in here, you can see update the alignment of voxels to the view. This is the part that actually tries to, like, keep things aligned. And you can see that it's going to do, when it detects that something, when it detects that the camera has shifted away from where the voxels are, it shifts the voxel and tries to align the lighting voxel to wherever the view is viewing. And the reason for this is because lighting is very expensive, so we only want to compute lighting just where we can see. We don't want to compute lighting anywhere else. And you can see these 2 set min corners here are the things that actually, like, figure out where the atlas grid and the spatial grid are here, right? The spatial grid being the thing we're actually using to do raycasting, and the atlas grid being the thing that we actually compute. The atlas grid will in general be smaller than the spatial grid because we only need to store and compute lighting values really in the area we can see, but we may need to keep a larger field than that for spatial intersections because we want to be able to cast outside of the visible region to see what we hit sometimes. So the spatial grid is potentially larger, right? So my question here is, again, it's the Z component that I just want to know about. How are we doing, like, how are we figuring out where to center the V component, right? If you look here, we've got sort of this notion of the voxel cell dimension. That is presumably just going to be whatever it is, right? The atlas's voxel dimensions are presumably set to something constant. We can step in here and investigate them, certainly. But then you can kind of see it trying to compute, like, where it's going to align these things, and presumably to actually set the dimension of this. I assume that the actual dimensions of this were kind of just determined by how many cells there were and what the dimension was. It's going to set the position of this relative to the camera center somehow. And my concern is that I don't know whether that's going to be set appropriately for what we're currently doing if we reduce this down to one voxel height, right, with no Z stacking. I need to make sure that it's actually centered around where the player is, which would be a trivial thing, and obviously would be what was happening if we had started out saying we're just going to be 2D only, but because we were always 3D, that probably isn't currently the case, right? Now, fortunately, I don't really have to guess. Now that I've looked at the code and it's working the way I think it is, right? Nothing particularly weird. I need to take a look and find out more specifically here. Can I, just draw where this lighting bound actually exists, right? Like, where is the lighting actually occurring? And to the extent that we want to do that, I think we already have the code in place. You can see here, there's a thing that draws the lighting bounds. And so this piece of code, just this one rect outline here, I believe we can make draw the part of we can make this draw like sort of the thing that bounds the area that we're actually lighting. Now, of course, I don't actually know. It looks like, though, maybe that's not true anymore because the light bounds don't get passed down here. So I suppose we actually need to draw them in here, which I suspect we do. Like, I suspect it's this right here, right? When we do push lighting render values. So this is actually the one we would want, which shows the hot voxel rectangle here. Which would allow us to see sort of where we're actually computing the lighting at, right? And you can see how it's completely black right now. And, I'm assuming that that's mostly just because, again, like the lights aren't actually, they're too, this boundary is going to be too narrow, right? So our first goal is to just get this working at only one voxel high. And also I can test to see like how, I can test to see like how flexible this is. Like if I set this up to something else like 8, would it continue working? So at what point does it actually fail in terms of setting the lookups, just to let us know if we've got bugs or something. So you can see here it looks like if you make it that high, right, it's still working just fine. If we drop it down now to 4, still fine, right? So it's just when you get it down small enough, it no longer is working properly. Maybe because we have some bugs at the boundary, maybe because the size is too small, so the lights are like outside of it, right? We just don't really know. But there's a too high one, and it's still working just fine. So I suspect really mostly what we need to do here is just to make sure that the voxel, the way that we're actually doing this light lookup voxel here doesn't have some kind of a bug in it when it gets down to 1, like maybe that's the case here. Or it could just be that this is now too thin and it's not picking up light sources for some reason, right? We really just don't know what the actual problem is. Here you can see I'm walking around now in there. So, let's take a look at this more carefully, and I'll set this up to 2 because that's the lowest version that's currently working. But again, we can kind of see that like there's no real reason that we need the lighting bounds to be particularly large, because even just setting it to 2, it looks the exact same now, right? Like the game really doesn't look particularly different this way. You can see a couple bugs. Again, with that height problem, as it moves up and down, you can kind of see that the lighting voxels, we're hopping in and out of, you can see like we're missing samples as we get too high. So, and the other thing that I guess I would say is, I also am not sure we want to drop to 1. We may want to keep it at 2 because we may want a high and a low sample on each tile to give it some, a little bit of range there. So to be completely honest, I don't actually know that we don't want to leave it at 2. But even just assuming, like let's assume we do want to leave it at 2, we still probably want to go ahead and try to fix the way that the heights work here, because we don't really want to move up and down in Z anymore. Like our new kind of rule that we decided when we just looked at what was good for cost-benefit analysis for the game is we just want to keep one level, and we're going to eliminate this kind of stairwell stuff, right? We're just not going to have it anymore because we decided it just wasn't interesting enough for the cost that we were paying. So assuming that we're going to do that, it means that now like the actual Z range of the lighting isn't really going to change. Those values are just going to be fixed in space. And we can't assume something like, oh, we're just going to pick some bounds between, -1 or 1 or something like that. We can do some kind of some kind of predefined value that just tells us what these Z bounds are going to be, and we're just going to go from there. So what that would translate to in practice is things like the sim region and other things like that are always going to end up, we're going to be taking Z out of all of their computations. And so what that means for the lighting system is when it goes through here to do like the update lighting, as it does, whenever we do this sort of set min bounds here, all of this stuff that we're looking at to see whether the center's moved and that sort of thing, we're not going to want to have Z be involved here at all, right? We're going to want to always adjust after the fact the values we're using to compute the alignment of the grid to just assume that Z is not a thing. So if you take a look at what's going on here, you can see we have like the origin P and the last origin P set up here. In theory, I think probably I would start by locking the like the sim regions to always have a constant Z. But then I assume we also, because this tracks the camera, I assume we would also need the camera Z's to be ignored. And I'm not sure exactly how I want to do that. You know, you can see here, like, there's an origin P and a sim origin P that are passed in here. And if we just start to assume that those are always zeroed, you know, I could do something like, say, that the sim origin P, you know, if you take a look at how these world positions work, there's like a chunk Z at an offset. If we always just assumed that all the Z values were 0, you know, what would this look like? So if we said, like, look, the chunk Z is always 0, and the offset Z is always 0, we're just never going to allow anything other than that to occur. So let's just 0 these out here. If we always assume that those are 0, what happens? Like, let's just look, because that's the entirety of the data that's coming in here in terms of alignment. So if we just take Z alignment out of the equation, where does that actually put our bounds, right? So you can see them here, and you can see that they are probably, well, I mean, it's really hard to say, but they're probably a little too, they're definitely oriented a little wrong in the sense that this should actually be moved up, right, considerably. And, you know, honestly, it looks like it probably is high enough, though. So mostly it looks like what we would need to do is just shift this upward, right? So when we look at what the origin Z values are there, it looks like, you know, it looks like the alignment of those is off in that sense. Now, there's a couple of different things we can do here, but the first problem that I have is I don't know who is off, right? If we're going to switch to a new unified, like we always assume we're on chunk Z0, are these on that chunk or not, right? If we take Z out of the system, it could be that the lighting is now properly aligned and these are all just high, because there was no reason in the past why they should be aligned, because we were just assuming, you know, Z can be anything. So we wouldn't have been like particularly careful to make sure these fell within our appropriate 2D range. So the other thing that I think I would like to try to do here is to draw in the sim region. So let's suppose that we take a... let's take a look at the outside here, where we're actually calling update lighting. So if you take a look at what we're actually passing for those values, you can see that after the diffuse atlas and the specular atlas here, we're passing the sim origin P, so it's this lighting sim center and lighting center, right? Those two. If we go look at where those are coming from, you can see them here. The simulation center, we should always peg to 0 as well outside of this, because everyone wants to do that now. And the lighting sim center, you can see, is using that camera simulation center there, and that also now wants to be pegged to 0. So probably if we move these outward a little bit, we can then also see to what extent those are aligned with the world, and maybe we draw like something in there that lets us know where that's happening. So let's try to back this out here and figure out like exactly where's the right place to make sure that these are always clamped. So if we take a look at the if we take a look at the simulation center, in fact, actually, these are the same, right? So these are always the same value, it looks like, sort of. I mean, not exactly. This is calling map into chunk space using the simulation center of, I guess, whatever the world camera rectangle is. So wherever the center of where you're looking is, right? So I suppose not exactly. But yeah, like, if you look at these two values, they're basically just being derived from each other, right? This simulation center is still the thing that matters in this case. And this is just looking at what the camera rectangle is that we're viewing and saying the center of it is going to be where that, where we actually take the lighting to be aligned. So this will take care of itself, but this wouldn't, right? Because that world camera rect, is going to be computed in a different way. So you can see it calling get camera rectangle at target with a focus Z here. And this computation is going to produce some kind of a up and down range, right? So let's take a look at how that's actually working. So get camera rectangle at target here, it's basically just saying, look, we're going to unproject the cube of visibility, and we're going to produce it here with a rect min max, right? So to be honest, I don't know that we really want to play with that. I'm guessing really what we want to do is just flatten these rectangles down to exist within a predefined sort of range, right? So that we basically like take the camera rect that comes out, but we want to flatten it so that we're generally talking about looking at a range close to 0 in Z. Because otherwise, there's really nothing wrong with this unproject that tells us the region that we're actually looking at here. Let's take a look at that world camera rect, where we're actually viewing that. We can push that as well. So this is going to be a white volume that's overlaid on top of what we've got here. So you can see here the two different actual rectangles in question. So what we see here is the camera view volume, and what we see here is the lighting volume. So don't ask me why they're quite so off-center aligned there. I think we decided that hopping backwards, you'd be less likely to, because the camera sees more forwards than it sees backwards. I think we skewed it intentionally there. So I don't think that's a bug. I think that's actually by design. But you can correct me if I'm wrong and go back and watch the tape. So looking at this, you can see that honestly, it's pretty reasonable, right? Like that actually looks, again, about right. And yeah, so, really, I think just making sure all of this stuff now exists at a predefined Z range, which would move everything down, and we'll probably have to change the world gen to move everything down a little bit, is probably fine. So the other thing I guess I want to do is at any given time here, I'd like to render what is effectively like just where is the 0 axis. So like, if I was going to do a -1 to 1 cube, like where would that cube sit? or maybe just yeah, I mean, I think that's the right thing to do. So let's suppose I did a negative 1 unit to a 1. Let's suppose I throw in a yellow cube that looks like that. And where is that, right? So this is just saying, like, where is the origin in our space so that we can see how we end up aligning these things. So what you can see there is that, yeah, we are floating a bit above, and, well, you know, not really. I guess it's not that much above. It's hard to say. A little bit above where the 0 region is. So if we were to sort of align these things directly to 0, you can sort of see we would be right in the middle boundary of that, which, you know, honestly is not that far from where we are at the moment. But if we were to do that, you can kind of see how we would need to make sure we span enough on either side to make sure that we're, you know, within reason there. But, you know, not too bad, right? Not too bad. Okay. So now that we have, and you can also see as we move around, you can see how the origin shifts. Remember, we use a relative origin so that we never run out of float precision. We're always centered around the origin roughly. So as you hop around the game, as you can kind of see, the outside of the game shifts the origin in order to keep that space, you know, relative properly. So my guess here is that, yeah, if we just kind of first lock the simulation center Z and then lock the lighting center, well, the lighting center will sort of automatically lock to it, that should pretty much do it. So in terms of simulation center, to be completely honest with you, I do not remember exactly how we set up those. I think the simulation center just gets shifted around as the camera, like we basically have a camera update routine that runs at the end that's like, I don't know where we call it exactly, but it happens somewhere in here. Update camera for entity movement. Update camera for entity movement is really the place, I think, where we shift the simulation center around it all. So yeah, like if you take a look at how this works, you can see that the camera itself moves around with this map into chunk space for camera P, DP, and target P. The simulation center part of things, I don't know when we actually update that for it. Let's find out here. Right here. So you can see this code here when we see that we're inside a room. You can see that the simulation center, when we map into chunk space, it's basically always pushing this align to movement voxel version of the simulation center. So it's always kind of taking this room volume min Z as simulation center. I want to say that we could literally just zero that out. So, you know, this is how we used to do it. And now we can literally just say, we're taking Z out of the system. And I think that would be it. I think now, no matter what we do, we would never shift upwards or downwards, right? For simulation center. So taking a look at it now, right? Again, the simulation center itself is not being drawn. So we may want to, I mean, it sort of is that 0 box that we've got in there. But the simulation region, I guess I would say. So if we want to show the simulation region, I believe this right here is what does that. Although it looks like for some reason, yeah, it does the bounds on XY. So I think this is, probably not exactly how you'd want to do it, because we're sort of already assuming that it gets centered around 0, which we kind of know the axis system is. So yeah, I mean, I guess what I would say is that is showing the simulation center, right? Because everything is centered around the simulation center. So as we hop around now, we should be always pegged to 0, so there shouldn't ever be a simulation center value where the Z is anything other than 0. Which means that as we go, like, for example, down into lower levels now, it shouldn't shift. And you see that it doesn't, right? It used to. So now we are going lower down. And the actual simulation center should not, we won't even really be able to see where we're going, but should not ever shift downward to follow us. And you can see it doesn't. We're down in this second level now. And you can see that although the camera rectangle clearly is shifting downward, right? The simulation center isn't, right? So I think that's step one. Step two is that we don't actually want the camera. So when we do the camera rectangle that we pass into the lighting, we don't ever want that camera rectangle to have that offset either. So I think what we probably want to do here is, again, head that off at the pass so that when we do our lighting values and we are computing those two offsets, one of them we know is always pegged to 0. The other one we should also make sure we constantly peg to 0. And so if we look here at the simulation bounds, we know that these should always be pegged to 0 properly. When we get down to here, this part, this get center world camera rect, that may produce an offset in Z. And so at least for the time being, I'm going to go ahead and just peg that so that the chunk Z is going to be 0 and the offset Z is going to be 0. Just to make sure that now the lighting rectangle is also properly always floored to 0, which will give us something that should always float right sort of on that boundary. Now, one of the things that you can see here is that the way these two things span is going to have to be adjusted slightly. And again, that may mean adjusting this stuff, or it may mean something else. Right? We have some flexibility in how we do this. But if you look at what's happening now, you can see that the lighting rectangle is properly sort of floating at the Z equals 0 area, and it can't actually or shouldn't be able to move up and down, right? So, it can move sort of in other directions. You can see there's a bit of wiggle there, which I'm not sure exactly what that's from. The hopping the hopping introduces a little bit of bounce there, but it doesn't appear to be Z bounce. I don't know. Maybe it is Z bounce. Let's make sure. It shouldn't be. It's kind of hard to say, right? But at least in theory, hopefully, we aren't getting any Z bounce now, because the offset in Z should be zeroed. It shouldn't really be possible to get something that's not zeroed out there, right? But that's the only thing that isn't derived off the simulation center. It's because of the world camera rect part that we could get a Z offset there. So this just prevents that from happening. And then, of course, this part should always be pegged to 0 now, because we don't allow the simulation center to ever be anything else either. So what we can do here is we can put in some asserts. Like, for example, I can assert that the lighting sim center here, that its chunk Z is always 0. And I can put in another assert here that the offset Z is always 0. Just to make sure that we're actually getting that, like that we're not somehow introducing some wobble. In fact, I could do that in a more opportune place as well. What I could do is actually go to the update lighting call. So when it gets passed in here, in fact, we could assert that we're never getting anything else from our sim origin or our lighting origin, right? So neither of those two things anymore is allowed to have a Z offset. So, it's just not going to happen. So now if we run that, we should be able to get like a hard crash, like it would assert and stop if any time anything was non-zero. So it looks like it's not, right? So we may have to do some other tweaking to it, but now we're at least fairly assured that we're not getting any kind of basically any kind of errant motion in Z. All right. So we now have to decide how we want to actually structure this. I would say that I don't have a particularly strong opinion about where I want the origin of the world to be. Like what should be the lowest z value that we contemplate being able to see. So my feeling is that we just make that be 0. So in other words, anything that's below 0 will not be tracked, right? So we just assume that maybe the world is built a little bit higher than 0, and if there was a pit or something, that pit it is just like a blackness at 0 or something. And so things don't really get lighting when they fall. If they were to go past 0, you just get the lighting from whatever was at 0. You don't keep getting lighting going down or things like that, right? So again, that's less realistic, but we're sort of saying like we're taking z out because it just doesn't give us enough bang for the buck there. So let's go ahead and actually sort of make that assumption. So what that means is that the lighting voxel is kind of aligned oddly. It appears that when you pass in the z at 0, it's treating that more as like a center point rather than a minimum, right? And that makes some sense for the other components, but it doesn't make a whole lot of sense for z, right? And so when we look at what happens here, we can sort of simplify a bunch of these things because now we don't have to have, so, for example, when we did block copy atlas, you can see in here we've got a whole bunch of stuff to handle like z, which now we would no longer have to do, right? So this sort of stuff would simplify, certainly, because it removes one entire set of the loops here. We could simplify a lot of this code. Now, I'm not going to bother with that because we could only be introducing bugs at this point, because we know that stuff works for the full case, so we don't really need to get rid of it. But what I would like to do first is say, well, okay, let's figure out how this is aligned in z and kind of change it a little bit so that it's always aligning ourselves to 0 and up, because it just gives us something we can be more assured of it. Now, saying that, maybe that's wrong, because since we're providing a center for all the other axes, maybe we want to provide a center for that too. I don't know. It's hard to make that call. So we could actually also say the opposite, right? Which is that we are passing in 0 as the center, and we kind of go up and down from there. That's also a plausible thing we could say. So maybe, that makes more sense. Let's take a look at this code first before we decide. So, here's the alignment code. It first says, look, let's find out if we were to take the origin P, which is where we want to compute the lighting, let's find where that offset is, right? You can see it computing the offset here. And then it says, well, where was the last place we did this, right? So it just tracks the center. That's all it's doing here. And then moves the voxel based on the movement of the center. Makes perfect sense. No worries, right? That would be the same no matter what we did, because that's just tracking relative movement. So the point, whether we pick the center or the corner or anything else, doesn't matter. As long as it's the same point each time, that code will work, because it's just sliding the voxel to match the world space. So really, this is the code here that we're talking about. And what you can see is this is the part where we compute those corners. You can see us doing a minus 0.5 of the hot dimension. So you can see us doing that computation as coming out from the center. So I guess what I would say about that is probably we just want to keep that. Because it's just a simpler computation. So we probably do want to say 0 is like the center point. And so the world expands a little bit up and a little bit down from 0. And we just kind of change a little bit, like when we're looking at something like the room gen code. Right now, things are sort of skewed upward, and maybe we just don't do that anymore, right? So when we're talking about figuring out where these walls actually occur, we, instead of what we're doing right now, we sort of shift them in another way. So, like, for example, when we take a look at how the p-value is getting set up here, you can kind of look and see how this is some pretty crappy code, but you can see get min z center p, right? It's asking for a tile. Where is the center point at the minimum z value? It's going to come back with this. We can sort of say, well, all right, how were we defining these tiles? And maybe what we need to do is say that these tiles are defined as being a little bit downward or something from where they were, so that things are aligned a little bit differently. If we take a look at get min z center p, you can see here where we point to the tile, and we want to get the total volume of this tile, right? Here is our definition for what a tile consists of. It's like wherever the relative index of this tile is the minimum p-value times the tile dim. And so the relative index z, right, like if it was 0, would end up being at 0 for this particular thing. And, you know, really we probably want that to be offset a little bit, right? So the total volume, total tile volume here, like this probably wants to be offset by some value if this is the minimum p for, you know, for this tile. And another way we could look at this is these values, if we're going to take z out of the equation, maybe these values are always cold set, right? Like maybe it's always -1, you know, to 1 or something like that. I'm not sure. If we look at the floor height, we have a, I'm not sure where this value actually gets computed, but we have this concept of the typical floor height here. And the typical floor height is just a thing we picked based on like, okay, how many meters should this be? You can see that it's 3 of whatever the fundamental unit is, right? Like that's how big this thing was. So what we presumably want to do here is have that value be reflected in that, like, it should be basically -half of that and positive of that, right? So the tile dim value here, we really want the z to sort of be centered around that in a way, right? So, you know, maybe the right way to look at this is to say, well, it's -half. So it's, if it was centered around this dim, it would be something more like this. Right? I also don't really know why this is being computed this way. That's a very strange way to compute this. You know, this is just kind of weird code. Like, normally, wouldn't you just do this? I mean, right? The max p is always 1 tile dim away from the min p, so why you would multiply them both for no reason, I have no idea. So, you know, I would assume that this is how you would normally do it. So, yeah, I don't really know what was up with that, but, you know, you got me. So anyway, looking at how that's aligned now, you can see that excuse me. You can see that we now have, first, that's a bit weird. I'm not sure why the lighting looks like it's down there. we're gonna have to take a look at that a little more carefully. But you can see now that everything is sort of aligned a little more sensibly, where we're going positive and negative of the, if this right here is the origin, so z equals 0 is right in the middle of that, right, is the way to think about that. Then you can kind of see how now the world is sort of built a little more sanely around that value, right? Now, it's not quite what I would like, because probably the floor should maybe be more around -1, would be my guess. So we're not quite as aligned as I would like, but we're more aligned. And also, coincidentally, the lighting now works around. The only problem we're getting is for some reason we have a weird, like, the camera is not actually aligned to, like, where the camera is looking does not actually seem to be aligned to where the world was constructed and lit. So we've got some kind of a bug with the camera thing there, but that's all right. Well, we're getting there. We're modifying one thing at a time, right? So it seems straightforward, relatively straightforward, right, to take z out of the equation there. And, it's not immediately clear exactly how we want this code to function, but this seems reasonable, right? That seems reasonable. And we can look into this a little bit further. So we could start to say, like, all right, this relative z index gets taken out of the equation as well. So, like, we know, for example, that this is not going to be a thing. Like, there's no rel index. So on the tile, right, when we look at the relative index of this thing, what actually tile rel index? Where is that? That's in edtile. Yeah, this guy right here, right? So the relative index here that we're using, we know that that will always get pegged as well, and that we don't really want to iterate over any of those values. It's just going to be rel index x and y. And again, we'll slowly peel that off. Like, we'll probably change the gen v3 here. We'll change that from a gen v3 to a gen v2 at some point, and just remove that third component entirely because it's not going to be involved. So, yeah, okay. So let's take a quick look, because before I go any further, I'd like to figure out why the, remember, the things we're looking at here is, this is the lighting bounds, and this is the camera, like what the camera says it's looking at. And I'm not quite sure I understand why these two would be offset in the way that they appear to be, because if we look at the camera, I mean, maybe this is just a case of the camera offset is computed, like, we didn't really look at how that was being done, so maybe it's just a case of forgetting the specifics of that. But if you take a look at how this works, you can see the simulation center here we're using directly. We know that that's aligned. We're looking at that that yellow cube. And so we know that everything's presumably working properly here, except for this world camera rect. The world camera rect is just doing the get camera rectangle at target here with the focus z, and this here, this focus z equals 0.5 times world mode camera expected focus min z expected focus max z. So this here is presumably, like, erroneous. The way that we're thinking about this is not correct, right? So what this function is doing is it's saying, at this distance from the camera, please compute what we would see. And, I can understand why we were doing that, because we imagined we were going to have complete freedom of how far z would be and so on. When we pass this value in, I don't actually know. Those are presumably camera relative, right? I don't actually know. Let's take a look. Because I'm not sure. So, okay, you can kind of see a bit of a oddity here, right? The expected focus min z and the expected focus max z is getting set based on where you are. So you can kind of see why this would be wrong. So these actually now want to be pegged values. So yeah, I mean, you can see pretty much why this is broken. Because if we're taking z out of the equation, this is still trying to compute some bounds about where the z is going to be focused on, right? And you can see us doing a bunch of work here to do stuff like setting the camera z values, because we were using some dynamic alpha blending to get rid of like floors that were above and below us. All of that can go away now, right? We don't actually need that code anymore, which again is why I say like it's going to be good to remove this code because it was extra complexity that really wasn't getting us very much. So yeah, so this code doesn't really need to happen because it actually isn't camera relative. It's actually literal in the world. And so what we're expecting now is that, look, we're just focusing on Z0. That's the focus that in the world from now on is at Z0. We're never going to let it go anywhere else, really. That's just where it is. And so now what we need to do is figure out like where that's going to be. It's a little bit weird that that didn't produce something centered around here. So that focus value must not really be world relative. I'm not entirely certain, because that's a bit strange, right? If we look at that world camera rect, that computation, if that's world relative, we should be able to produce, we should be able to pretty much plug in any value that we want here. So that's a little bit odd that plugging in focus Z of 0. So maybe that's not, let me look at how this code works just so I can see how we were computing it. So get camera rectangle at distance. It's this one right here. So if we do world distance from camera Z. So, okay, so that is camera relative. I'm so confused right now. That is camera relative. It didn't look like it was camera relative, though. So how let's look at how are we computing this here? Those are derived from target expected focus, right? So target expected focus, room focus Z, and entity focus Z. So all right, room focus Z and entity focus Z. How are we updating those? Okay, so it is relative to the camera, right? All right, so what's the focus Z here relative to the camera? Is this measured? So we would need to know the camera arm here. So you know what, I could say, I could leave this quote unquote computation in place. Although I think we probably just want expected focus Z to just be a value on its own. So maybe we'll just say, look, the focus Z is this, and then we'll eliminate that that actual value. So from camera, we will say world camera. Where was the if this is our camera? Why world mode camera expected focus Z? That is not the actual camera. Again, too much complexity. You can see why I want to do one simplification pass. So it's the game camera is the thing that generates the camera because the actual camera is just for rendering, right? You can see here we've got all of the target expected Z, all that stuff. So this I'm going to simplify down to just expected focus Z. And that we don't really need to compute every frame. It's just going to more or less be, well, I mean, I guess we do if the camera like pulls back or goes forwards. So I suppose yeah, I mean, maybe we do kind of do it every frame for that reason. But that's all we actually need. So if you take a look here, you can see there's this camera arm concept, right? Which is like the camera Z value, which is presumably just something we build up here. Yeah. So the camera Z value, well, we're even just passing it in, right? So when we do update camera for entity movement, you can see us passing in the camera Z here. That's the camera Z axis, right? So I would say we just back out all of this code. We just nuke it from orbit. Because the only person who cares about this value now is going to be the person who sets that lighting offset value, right? So when it tries to determine what the camera rect is, this right here, we can use the camera Z that we ourselves computed to figure out this value trivially. Because it's just wherever the camera is, it's dot producted with that axis, right? It's just a measure along this axis how far away the camera was. So we no longer need to do this because we're not actually going to be, we're always going to peg our Z distance. So I think that basically simplifies all of this code. Like all of this code will now go away, which is great because like I said, it's too complicated, right? So yeah. Although I guess now that I think about it too, though, the only thing that we do want to do is we probably still do want to pass it in after we trim all the code, because in order to produce the new target location, we would still have that Z arm come out of it. So it still needs to kind of know like how far it should move out based on what it's looking at. So I'm gonna just trim this code really quick here, but then we still do kind of want it just for this. We don't need this anymore, right? But we do kind of want to trim all of this stuff. So I think all of this goes away, the entirety of it. Yeah, none of this still exists. But I spoke too soon. We still do want the camera ZX, so because it needs to know how far out. It needs to know how to move the camera, how far away, how far pulled back it needs to be, right? So that's okay. So now we just need to take this piece of code here. We don't care about any of this. So this focus Z Mac and the fog params, we're not really gonna do those anymore, right? But we can still set these. I don't know exactly what the values here want to be, but I don't know. These can be set to like something fairly wide here temporarily, but I'm going to put to do in here and just say simplify all this code now that Z doesn't vary. So we're going to do a few simplification passes here. Put the camera Z back in there. And yeah, we don't care about any of this stuff. It's just printing that stuff out. And so now I just need to go and make it so that we compute that camera Z offset, this expected focus here. So the camera Z would just be the inner product, the expected focus Z, so this value that we want here, the expected focus Z, which we can get rid of that in the actual game camera. We don't need it anymore. This is always known. We can just say, look, wherever the camera actually is, the expected focus Z is just the measurement along the camera Z axis of that. So we just need like the camera position here, right, is all we actually need, because that back from 0 is all we really need to know. Now, the problem that we're going to have is that we don't actually, the expected focus Z value there, like how far back it's going to be, we do need the target and the world position. We need to measure those. So we need, we effectively need like target, I guess we would need like camera pose minus camera target, right? Can't quite spell today. We would need like the camera position minus the camera target for the expected focus Z value. And in order to produce that, we presumably already have presumably have already computed those camera values here, right? So, like for example, in order to set the camera transform, we would need this information, right? So camera 0t, I assume, is the value that we actually are looking for here for. Just quick take delta from sim. So subtract remote camera P from camera simulation center. So yeah, you can see like delta from sim is where the camera actually is, right? It's the camera P here. And I guess we don't at the moment. I don't know that we look at the target, but I guess we know the target is always at 0 anyway, so we probably don't care because the X and Y displacement, well, but we kind of do want to remove those because we only want just how far away it's going to be, and it could add to the appearance that it is further away along that axis, right? I mean, is that true? Or is that going to take it? Is it going to be entirely... Yeah. So I'm not 100% sure about that. So I think I'm just going to recompute the value here just to be sure. Because I don't want this to be at all wrong. So I'm going to do like camera target to camera, something like that. So that we can take a look at the game camera here and say, look, we've got a P, we've got a target P. And maybe, I guess I also don't really know, though, to what extent this is doing sort of a chase movement. Like, if this is interpolating towards here, then the camera P, as it currently exists, I guess we don't really know. You know, we don't know how far it is in X and Y. Ugh. Although we do kind of know, so I guess all of this, again, because we know that the camera has to, it's just the intersection with the 0 plane is where it has to go. We could just ask for that intersection from the, you know, from the p-value, right? So I suppose we, just because we don't have the target p-value, I suppose we could just say, well, if we know where the camera is looking currently, we know how far away that it's going to have to be to produce that z-value. So it should be possible for us to correctly set this, because again, we know that no matter how the camera moves, because the camera does change its position in z, we're always looking back towards the z0 value. So in theory, right, we should be able to just say, well, the ratio between the just a straight, you know, this, the ratio of movement between the z vector, just pure z, and whatever the camera's current z, like the direction the camera is currently looking, that's just going to be the camera's z's z value, right? That's how slowly it goes forwards in z. So whatever the height is of the camera, right? Whatever the I think we called that, what, delta from sim, right? It was called delta from sim. So delta from sim, where was that value? It was right here. When we compute this delta from sim, which just says how far is the camera off of 0, because we know that this is always 0z, right? So how far is the camera off of 0? We would know just right from that, we immediately already know, just by looking at that z vector, what the distance to the z plane would be, right? So the delta from sim's z value, that's how far in z, just vertically, the camera is off the ground. And the order of the subtraction there, when we look at delta from sim, it's going from the simulation center to the camera. So it's a positive value, right? Because the camera is higher than the 0 plane always. So when we look at that value, we know that this is a positive value. We know that the camera z, presumably if this orientation is, you know, a right-handed coordinate system, we're going to, I guess I don't really remember exactly how we set it up, but I believe z comes out back towards us in the screen. So we're also talking about a value that would be coming up away from the z-plane there. So assuming that those are both true, then really all we're talking about is like a divide here, right? the amount of time it will take it to intersect this plane, right, is just going to be how far it has to go divided by how fast, effectively, it goes along that vector, and that would be the expected focus z value, right? So I think that's pretty much it, but, you know, I could be very wrong about that, if that makes sense. All right. So let's try and get that debugged properly, because I think that's all we really want to do, is to say, like, look, that's okay, so that's going to be like our focus value, right? So let's take a look at this code and see how that actually works. I also don't know if this is supposed to be negative, meaning negative motion along it. So if we look at get camera rectangle at distance, we have to kind of know which world distance from camera Z. Because it's phrased that way, I would assume that world distance from camera Z effectively means that the value is going to be positive, but I don't actually know that, right? So we have to go kind of verify that that's the case. When you look at unproject, for example, and you look at this world distance from camera Z, you know, what is that actually saying here? So it's creating a, from the origin of the camera, basically, it's subtracting the distance times the Z. So yeah, so I think this value is positive, right? I think this value is positive. That's being passed in here, but I could be wrong about that. So let's take a look. If I switch to a debug build so we can inspect these values more, just turn to the O2 to an OD here. I'm going to set a breakpoint in there somewhere. Let's get a little more room here. I'm going to set a breakpoint in there so I can inspect how that code is functioning, and we'll just take a look at it. So here is us reaching the delta from simline. Let's take a look at what these values work out to be. So we've got delta from sim, and we've got camera Z. So here are those values. This is what you would expect, right? So if you take a look at what we're actually getting here, you would expect a camera Z value to not have any X component in it, because we're looking straight down. We're not looking, there's no slant on either side. We're just slanted in Y. So we expect there to be a Y value, relatively small, a Z value, relatively large. That's exactly what we see. So this makes perfect sense. Let's take a look at our delta from sim. That is not what I would have expected. So that's confusing and may be a source of our errors here. Maybe it takes the camera a little while. Okay, so it looks like it takes the camera a little while to chase where it should be. All right. So now the camera it's negative 2.8 back in Y, but its Z value is 0. So that definitely means I screwed something up there. Probably in my overzealous setting of Z's to 0, I must have accidentally eliminated the camera's ability to move up off of the floor, which is going to cause a huge problem, right? Specifically for this. Because if this is 0 and the camera's like flattened to the floor, we've got issues. So I'm not sure what, maybe I'm thinking of delta from sim incorrectly. Let's take a quick look at how that works. But yeah, I mean, looking at it, yeah, it's definitely not good. So if we take a look here at update camera for entity movement, just thinking about what the Z offset's going to be, let's go down and take a look at how this is being computed here. So in terms of where the camera's going to end up, So I guess this value here is set per room about how far away you want the camera to be, but that's okay. That should be right. I mean that seems correct, right? Um, so I couldn't say, I really couldn't tell you why that was coming out incorrectly. The only thing I could really think of is if the room centers are just set totally wrong, so that it just so happens that it comes out to a 0 value. That seems unlikely. But obviously, we don't really have to speculate. We've got a debug build here, so I mean, heck, I'll just take a look. Because that part is like, we do have to make sure that the rooms are set so that they make sense in that way, and we don't really know exactly what they are set to. So let's take a look and see, just so we know about that piece of the puzzle. Because, right, each room in the world can have its own sort of like, how far do you want the camera pulled back. So if we step in through the code here and we take a look, I'm going to go ahead and say we can skip to just like when we find out a particular in-room value here. We'll see. Okay, so it looks like the problem is that the room bounds are wrong in Z, so it looks like you're not in any room at all, right? So maybe that's just a separate problem that we have to fix, and maybe that could be our only problem. Probably not, but it could be. So when we actually create these room bounds, I guess I'm not sure where we were doing that in the room gen code. Obviously, when we create this stuff, we're sort of procedurally generating these things, so we don't really have any particular, we never really thought very much about where they would be in Z, because again, we were never thinking that it would just be flat plane. So I don't actually know, like how this particular thing is set up to work. So one thing I might say too, we probably do want to adjust this, but the other thing we would probably want to do is when we take a look at that update camera for entity movement, when we're looking at the test bounds, we probably don't want to use Z anymore either for that inclusion test. I mean, really, we probably just want to consider anything in the XY. Just use XY as the thing that determines whether you're in it or not, right? But so if we take a look at how the layout code works here, you can see us making sort of these, volume creation for rooms here. When we actually go to set the collision volume of a room, which I assume may be in the room gen code. I'm not sure who sets the actual room, like who actually creates the room collision volume itself. This is not it. Camera room. So you can see the get room volume call, and it returns the room dim here, and uses the camera room P here, which is getting the center of the room volume. So when we set this room, this whole thing again is, this whole thing here is all using this rectangle 3, setting this room dimension here is probably wrong. You can kind of see like how this is getting set, right? So really the Z bounds on the room dim, and I think, I'm taking this really slow, but again, I want to rip out a lot of this code because it's complexity that doesn't need to be there. But if we take a look at how the room dimension stuff is working now, you can kind of see that, like, we don't really want room dims to exist in this way anyway, right? So, like, the min room P, max room P stuff here where we do, where we adjust this stuff, you can kind of see that the Z is just not what we want, right? So when we actually come up with the room dim here, this stuff is just not, this is not helping. So presumably this most straightforward thing to do would be to, although you can see the add radius to, it's weird, there's like a grid region versus grid rect. This is a bit weird. But, if you imagine the room dim here, if we just move the min room P Z, or, we could probably just do this. So if we want to add, a radius of, a Z value of like 5 in both directions to make the room larger, right? What is this? Looks like a typo there. There we go. We should be good to go, right? And let me take a look at this code now again. Yeah, so now it does correctly find a room, and in theory, we would now have an actual camera position. So let's just take a quick look at that before we go any further. Okay. So now it looks like everything's square. So it looks like the problem that we were having before was just that, yeah, you weren't considered to really be in a room. But now all of the bounds appear correct. And wow, check out that frame rate. This is the debug build. Talk about the lighting getting faster. Remember how slow the debug build used to be? Switching from 3D to 2D, not just in terms of world complexity, pays a lot of dividends. It's not subtle, right? It's not subtle. Yeah. So here's the lighting again. Let me just take a look here at, I'm curious now, profile wise. Yeah, I mean, we're like locked 60 frames a second easily now. And we haven't done anything. Like, all we did was reduce the lighting computation to being the 2D portion, and off you go. So we still haven't done a lot of the stuff we want to do here, but we're getting closer. So that's good. We now have to fix like our fog. So do you see how there's like a haze over the world here? Our fog parameters are now kind of set incorrectly because we're not really taking any care to set them. And, we don't necessarily want to get rid of the fog code because, we don't really know if we're going to want, stuff like that. Just a simple way to, like, add some fog in the game or whatever. We wanted to be able to do stuff like that, potentially. So my suspicion would be that we don't really want to eliminate that, out of hand. So next thing's next. We want to go set that fog code so that we don't, so that it's properly bounded to a reasonable region around where we're actually looking in the world, right? So you can see here's our fog value stuff, and my assumption would be that since we know the expected focus Z, presumably we can use that. We are computing a real focus Z value now, right? That we're using to we are computing the expected focus Z value, and we're producing it correctly, right? So up here, it's free for us to just say, well, we can do that right off the bat, and then we can sort of like set the fogging properly based on that. So again, I don't really know what these values want to be, but we can certainly set them to something more sane for the immediate moment than what we were doing before, right? Now we do need the camera Z value, which it looks like we don't extract yet at this point. So we just have to move that down below. Maybe keep these things together. Like here's where we extract camera values, and here's where we compute values dependent on those. But yeah. And maybe I'll delete this to do as well, because we don't know that Z won't vary. Like the camera does pull back and zoom in. We're not going to remove that particular value, right? So now we can see we don't have the weird fog overlay because, you know, like as you can see, we've recomputed the value to be more correct. So the fog code's still in there in case we want to use it, but now it's, you know, it's not having the same erroneous range computation. So, you know, we're slowly but surely moving towards where we want to be. And let's go ahead now and keep going forwards along this axis. So we still have a bunch of things that we need to work out. So one of the problems that we will have right now is that we don't actually have any coherent theory for where the light probes are placed relative to where the actual geometry is, right? So we're not really taking any special care. Like right now, we're not even drawing where those light probes are. So we have no idea like where these light probes are located. And, you know, probably we want them to be aligned to this grid in some way, or, you know, we want them to be doing something intelligent as to where they are. And we don't really know what that is at the moment. And with specifically, we want to make sure that the Z height, like where the probes are located in Z, is going to be pretty important, because we know that we're only computing 2. So we would probably, you know, all things being equal, we would like our Z probes probably one at around floor height, like a little bit above the floor, and one like a little bit below the ceiling or something, is probably where we want them, because anywhere else is really just not giving us very much valuable information, because we know that everywhere that we sample these light probes is going to be basically in that area, right? So there wouldn't really be much of a point to it if we place them in any other way. So what we probably want to do is now actually go make sure that that placement is at least somewhat sane, right? And I don't really know to what extent we left in the code for showing where those atlases actually are, but I think we had some code in there for that at some point, but I guess I don't really remember. So sorry about that. So let's take a quick look. Let's see, do we have any code for this? I don't know if we do. It looks like debug draw octahedral values. It sort of does that. So we could use that. That looks like basically what we've got. That looks like what we'd mostly be looking at. Yeah. So, yeah, I don't really know. But I think that's probably the most sane one. So, yeah, like maybe we try to actually just call debug draw octahedral values. And yeah, I mean, I don't know. Debug draw octahedral values. So it looks like at least we seem to think that that's a plausible call that we could make. So I'll, try running it, and we'll see what happens. It looks like we don't have enough. So let me actually see where that assertion actually is firing. I like the new timer. What do you guys think of the new timer, by the way? I just want to see where this is complaining. So it looks like actually this is just kind of messed up, though. Like the get tile unclamped is maybe bogus, right? So it's like this is actually just kind of buggy. What's the deal here? Well, that's obviously wrong. Hold on a second. Okay. Yeah. Yeah, no. So let's fix this code because this is just picking complete garbage values. I'm gonna go ahead and say that now that we don't have stacks of these things, maybe we can draw them all, because there wouldn't be too many for debugging purposes. I don't know. That may be too much. I'm not sure. But if we did say something like this for starters, that's an easy solution to the problem. Because yeah, that was just some random debug code that picked arbitrary placement. Yeah, so there we can see, in theory, those locations. Let's go ahead and switch back to O2, so we don't really have to debug that now. And we can kind of see where these voxel values are sitting. So here's the lighting voxel. You can see that it's actually not bad. Like that's a pretty reasonable placement for these. I would say actually, it's not bad. My main complaint with it would be that at least currently, they're too high, I think. So, maybe they would want to be, I don't know, are they too high? Maybe that's not true. Also, the fact that there's that few of them, I think also we probably can just do this. I don't know that we need to clip out that many of them. We might just be able to draw them all now. I lied. All right. Hey, what can I say? I was being overly optimistic. Let's try a quarter of them. There we go. So okay, so you can see all the light probes. There they are. And you can see the lighting computations that they've got. I would note that there seems to be some pretty weird stuff going on. So I think we have some kind of buggy behavior occurring in here, which, we'll have to investigate. But like if you look at some of these light probes, some of them don't make a whole lot of sense. So it may be because there's hidden occluders in the ceiling area or something that may be occurring here, right? So I'm not sure, but like it's not, there isn't a lot of explanation as to why that voxel is not picking up any light, right? So it looks like we've got some additional buggy behavior going on in there that these things are not quite they're not quite stepping through the world correctly or something, right? There's something amiss in there, right? And one thing I can do is draw those occluders. It may just be a case of like floating point jitter, but let me go ahead and draw those occluders a little bit better so that we can see them more cleanly. So if we were to do that, that would be in the collision code. So in the collision drawing code, if we just turned that on, like, here. So this lets us kind of see how this stuff is set up. But, if you just look at this, you can tell immediately, like, that's just wrong. You know what I mean? Like, there's no way that's a correct lighting value. These things can't all be picking up the light that's right here, and this is not. So we've got some buggy behavior happening now. And, again, this is probably as we kind of go through and try to clean out the way that this stuff is being computed, we're going to have to deal with the fact that these are a little bit wrong. Now, one problem that we may be looking at here is when we changed the way that the tiles were being aligned, we changed so that they were aligned on their center points now, which means that like the lighting voxel is shifted a half tile relative to where it was. They used to be in the centers of tiles, now they're on the corners, right? Now, that may actually be desirable, so I don't know that I necessarily want to fix that, because I may want to have them exactly in that configuration. That may actually be exactly what I want. So what I'd rather do is sort of work through the code and just clean up some of these, some of whatever these errors are here, right? Like I want to fix that so that I want to find out why we're getting no lighting samples on some of these grid points in a very like suspicious regular pattern, right? Like, you don't see any lighting values coming from these for some reason, but I don't know why. So that's like very suspicious, right? Big bright ball, little tiny not bright. You know what I mean? So we clearly have some debugging work to do there. But otherwise, I think we're getting into better shape, right? We're slowly making progress here towards something a little more reasonable. And I do really like the fact that the frame rate already is massively better just from that one change to two layers of light probes instead of like, the full depth of them. So again, making a lot of improvements just by reducing from 3D to 2D in terms of a world construction without actually giving up the 3D nature of what's happening on the screen as apparent to the player in really much of any way at all. So I do think it's the right call, bang for the buck wise, for what we've got. Okay, so given that, we have a bunch of things we want to do, and unfortunately, I guess I'm not sure exactly where to start, because we want to kind of go through these systems one at a time, and kind of clean them up and button them up a little bit, right? And so we want to start removing some of this complexity, and, there's so much complexity to pull out now that I'm not really sure where would be the most profitable place to start. I think I'm fairly comfortable with the decision because just looking at how much performance benefit we got back from just eliminating Z-layer, it's kind of crazy. And if you think about how much of a savings we're going to get in terms of code complexity, if you even just look at the lighting code, we got that performance benefit without actually optimizing with that knowledge. Because one of the things that you have to remember is we actually have complete light stepping tables that include stepping in Z. So like the compute walk table here produces values that include the possibility of Z stepping, even though now there is no Z stepping, meaning we can just bin things in one bin in Z everywhere and remove one entire type of voxel step from the entire system, right? So there's just a tremendous amount of benefit we can get here, and I'm just not sure. There's so many places we can improve by making this simplifying change that it's just kind of scary. Because, you know, gosh, where to start and what's the right order to do it in, right? So I really just don't know. And my guess would actually be, what would my guess be? My guess would be maybe we just... Maybe we just say something like... We now can just do straight... Yeah, I don't know. If we're just regressing to a 2D grid, because now we know that we just have a flat 2D grid and we can just do all of our computations on the 2D grid, we could also just say that from now on, we don't actually have to store a spatial partition at all. Our 2D grid is just stores what's the height of the occluder in that grid. Right? I mean, the amount of computational complexity we could reduce there seems pretty vast. Because we could just say, like, look, we're locking down to the 2D grid now, and that's just how it's going to go. And then all of our raycasting could just be directly on the 2D grid and doesn't have to actually do a pass where it even spatially partitions anything anyway, because it doesn't need to anymore, right? It knows it's just going to do grid stepping, and the grid could just be unpacked directly, right? So it's really hard. I mean, man, just thinking this through, it's really hard to say. The amount of simplification we could do there is so vast that, you know, like I said, there's so many potential options for us. It's hard to decide which one to pursue first because they all seem good. And so I'm just a little bit paralyzed by too many. This is a good problem to have, I guess. Too many good options at once means it's hard to decide where to start, and picking a good order will pay dividends because it will be less work overall if you do it in, you know, sort of a good order to begin with. Okay. I guess first things first. I would like to find out why we have a regular pattern of errant sample drawing. Like, what's going on with these sample spheres? Why are we getting this odd, like, you know, why is there this fake sort of occlusion happening here where, you can kind of see that for whatever reason there was no light hitting these samples, even though they're clearly pointing in a direction where they should have hit something. I mean, remember, we're using indirect lighting here, so that means not only did they not hit a light source, they didn't hit anything which even supposedly has any light at all. Like they didn't hit the floor somehow. So that suggests to me that they are somehow being maybe erroneously marked as being inside like some kind of a volume, so that they can't cast. Like maybe they're just having some kind of a they're hitting some kind of I'm not sure what the word is. We have tests in here to say if you are inside a volume or something, don't cast, right? There's basically a thing that tries to prevent you from wasting time casting out of a light probe that's like inside something. And the example would be like, this one in here. You can, there'd be a light probe that you can't see that's in here. I think we like detect that you're inside a volume and then don't cast light or something like that. And so it could be something like that. And I suppose it wouldn't be that hard for us to test because inside full cast, I believe this is inside here is basically the code for that. So, I think we could just say, well, if we just said if 0 and prevented that code from running, that would, all right. So that basically tells us that is what that's what that was. Apparently that inside outside check was totally wrong, right? So I think there's some kind of bug going on here with the spatial partition, like because of the shift in cell alignment or something, like we're not doing this correct somehow. Like we're doing a check, because the way this code works is it just loops through here, looking at the leaves of the spatial partition, looking at the leaves of the spatial partition and asking the question, do any of the things in the spatial partition in this box enclose us? Right? That's what's happening here. And if any of them do enclose us, then we just don't cast. So it thinks that some things in the spatial partition are enclosing, which means that our spatial partition is currently broken slightly. So something that we did with those Z changes is causing our ability to do our spatial partition, the code that tries to do the geometry for that spatial partition is now like wrong in some way. Because there's no way that that should just not be happening, right? Now, in terms of being able to draw the spatial partition, I don't know what we've got for that. We probably did some of that at some point, right? Because we would have needed to debug what that looked like over time, during grid build spatial partition, right? Like we would need to debug this code. And but I don't really see anywhere where we were drawing the spatial partition that we could re-enable, right? So that brings me to the first decision that we'd have to make here, which is, do we just say, well, the heck with it, we know we can simplify the way that these spatial things are working anyway. Do we just say we're not going to bother debugging that code, we're just going to vaporize it and replace it with a more straightforward cell walk, right? And that seems like the right thing to do, because I don't know why we would bother simplifying this code. I'm sorry, debugging this code only then to replace it with new code, which we would then have to debug as well. So it would kind of seem to me like the best policy would be to just simplify the code first and then debug the simplified code, because if we're going to have to debug it either way, it would seem, right, like that would be the smart call. So I guess we're just gonna do that. That's my call. It might be a bad call, because sometimes it's a bad idea if you don't have the current state of the code working to switch to a new state. But I'm just thinking like, well, I'm gonna have to debug both of these either way. So yeah, right. So if we take a look at grid build spatial partition here, there's two steps of simplification we can make. I'm going to say we should make the removing Z1 first. And then the next one we can make is just having it so the spatial partition actually isn't a spatial partition so much as it's just a grid that records like effectively like the space that array can pass through or something similar. So if we just assume that the spatial partition no longer has a z coordinate at all, what's that going to look like, I guess would be the first question. So if we were to say that the spatial partition, as we see it here, and you can actually see it, you can see a grid leaf, right? You've got a box min, you've got a box max, and then you've got like color and emission and so on. If we are to simplify this down, we can still keep all of the 3D-ness of those so that we can have like partial occluders in grid cells. We can keep all that. And the main difference here would be that the spatial grid itself would just lose its Z stack, right? So like the indexing into this thing would lose the Z part of the index. You know what I mean? So as we're like stepping through here, you can see like it has this sort of grid index that's going on here. And this step just uses stepping from the table. So it just uses this dgrid, right? So in the compute walk table function, you can see here where it loops over, it loops over the directions that you might be going. Z positive and negative, Y positive and negative, X positive and negative. And then it goes in and looks at what the table entries are for that thing. You know what I'm saying? So if we were just to take Z stepping out of the equation, I like our little debug checks here. If we were to take Z stepping out of the equation, we would basically be removing these parts of the Z for loop here. And you can see we've got this flat index from function, which packs things down based on their Z index. So you can see like the index Z is right here. That would just always now be 0. Right? And the grid cell count in the voxel grid, its Z value would also always be 0, right? 1, right? So I guess let's just try to make this change. So when we in the lighting here, this is gonna be a bit of a nail biter. But when we in the lighting here go to set up the spatial grid, you can see the spatial cell count is the value that we're actually asking for. You can see this happening here. The atlas cell count, which is determined by whatever the voxel dimension, which is 2, right? this is all, well, you know, it would just produce 1 by default in Z, actually. So that will do the right thing, I think. Let's take a look. But to start with, we don't even have to clamp that value down because I think it will always produce 1 anyway if it's half the resolution of the spell count. So although this part here, atlas to spatial grid index offset, that part would not, right? That part would not. So let's take a careful look at this. I'm going to go into the lighting code here and set a breakpoint. And there we go. Is that only set once? Yeah. Just wanted to make sure that it's only set once, which is what I said before, but I was like, well, let's be sure that this only gets set once. So here's the voxel cell dimension, which is just the fundamental unit in all directions. Here's the spatial cell count, which is 14 by 10 by 3. So this 3 here, we really just want to set to 1, right? We want to kind of get rid of that. So I'm not sure to what extent that... You know, this part has to make sure that it would encompass all of the geometry, right? So the spatial cell count, 2 times voxel cell dim, you can see the spatial grid is based off of how the atlas is set up. It's twice as wide, right? Like, so for every we've been at basically a rate of 2 grid squares, like 4 tiles, 2 by 2, and so this would have to encompass all of the Z direction, right? So when we do the atlas grid here, this spatial grid would have to be, its Z would have to be set a little bit differently because we want it to encompass the whole thing, right? We don't really want it to remove anything. Whatever we push down here, it should take, right? And then this Z value should be 1, and again, that came from, because atlas cell count should be set to 2 here. So when this divide by 2, it will just be 1. So it's really this atlas to spatial grid index, that part right there, that offset is really the problem. So the atlas to spatial grid offset, this, I don't really know what that's even really designed to do anymore, right? Like, I think the basic idea there is that you want the spatial grid to include 1 tile outside of wherever you're casting, right? So I imagine, but don't know, I imagine that like that becomes a 0, so that it's always just 1 in that direction. And then the spatial grid's alignment, which I think we really we're gonna wanna draw, right? The dimensions of this are gonna have to be set carefully to make sure they include everything. You know what I mean? So I assume that there's something that would go on here that, that would, well, let's draw it first and then make sure that we're keeping it in some kind of a sane location. So solution, spatial grid, total bounds. And I'm going to draw that Maybe that gets drawn in green. And we'll just see. We will see. All right. So I think that makes sense to me. Like, it's designed to have an apron, and I think that's good. So really the only thing we need to do is make sure that the z-bounds span the correct sort of distance, which they don't currently, right? So if we look at how the z-bounds are set up, we want, in here where we do this dimension, we want to include enough height so that it encompasses the cell dimension, like, of z, right? We need to encompass 3 layers of z because we're not adding those in. So we actually want something like this, which is like spatial cell dim. We want to take what we would normally use as the dimension, and we want to make sure that it's like 3 stacks. You know what I'm saying? It wants to be 3 high. So, oops, that's a regular V3, not a V3S. So we want that spatial partition to be 3 high, and if we look at what it looks like now, hopefully it's more aligned. Although, okay, no, it's not. It backed it down from there. All right, so the alignment code does something weird with the Z there that I don't quite understand. So let's take a look at why it decided to do that, because I'm not sure why it would align it in that way. That's a bit weird. But we're looking at this code here, and, you know, here's how the spatial corner works. It takes the min corner, and it moves 1 cell dim off. Okay, so I see why, right? If it's going to move 1 cell dim off, then it's going to include that huge amount. So we don't actually get the benefit that we wanted there, right? So we need to do something here where we're going to move 1 cell dim off but only 1/3 of a cell dim off in the other direction, right? So, again, I'm not sure how exactly we want to do this, but it would look something like this. Right. So we just effectively be saying, well, look, the Z is handled differently than the other 2 axes because it just is the whole thing. There's no tile apron. It's just the whole thing, right? So that is now an aligned spatial partition that is now in the correct place, right? So, all right, you know, that's a start. It's not perfect, but, you know, it's a start. If we take a look at the walk code now, we need to remove the concept that you can really move in Z. So when we are looking at a sample, we need to just, yeah, like, the thing that I'm just not sure about is whether we want to keep the notion of the spatial grid and the atlas grid separate anymore anyway, or should they just be completely collapsed now? And I really just don't know. But I think I understand basically why we're having the problem too with the spatial grid versus atlas grid offset, because I think I said something wrong here. So these are not directions. These are the offsets of the probe point inside the spatial grid. That's what those actually are. And so, you know, it's how you would walk the spatial grid based on where you are inside it. So there you go. So Z in this case doesn't exist because you can't step in Z. So we want to pull that out as a next step. When we walk through here and we look at the remainder, there is never going to be a remainder in Z. It simply isn't allowed. You can only step in X and Y. That's just how that works, right? When we do get octant for, it's going to have to understand that we are doing that. So I'm not sure. That one's a little confusing. So I'm not sure exactly what that does. Let's take a look. So really the octant index is just something we use for packing the answers in here, right? And now octant index would just become quadrant index. It's just a way to load the table, right? So really that's all that is. This would be, instead of get octant for, you know, it's going to be get quadrant for. And we pass the remainder in here. We would assert that the remainder Z equals 0 because you're never allowed to have anything else, and we'd never shift that one up. So now, whereas before there could be 8 answers coming out of this, there's only 4 possible answers now. So the quadrant index is how we would pack these in. When we go ahead and do our testing for sample directions here, we're also going to have the problem that we go through the directional indexes to see which one is greater and all that other nonsense. We don't want to do that anymore either. So like the dimension index here is just going to be 2. We're not going to ever contemplate the Z value at all. And so then I would assume, I'm not sure what do we do with nvrad here. Let's take a look. Yeah, you can see like we're just computing those 2 values. So really, if we just change the dimension index here to 2, so we never check the other ones, we never really need to check this equals. That's just never going to happen because we know that it wouldn't matter. So that's basically saying if 0 and 2 are both the same, then it uses 2 and picks best dim 2. We know that's never allowed anymore because the best dim can never be 2. So we are pretty much always going to do this. Always. And we're only really comparing between the X and Y now, right? So we don't even really need to do like this T best at all. We can just look at the difference between 0 and the 0 index and the 1 index. So we could simplify this down quite a bit. We don't care about doing that here, obviously. But, you know. So I feel like all this is fine. The only thing I would be a little bit worried about here is that the ray direction, when we do this divide, we wouldn't have really conditioned it, but that's okay, it looks like. So I think this is okay, more or less, right? We want to make sure we never take that step. So when we get down here, I would just assert that best dim is not equal to 2. Like, you know, I could be even harder and say that it has to be 1 or 0. Can't be anything else, because it's only going to step in one direction or the other. And then the quadrant index is, you know, going to get followed through here. So there's our quadrant index. I'm just going to look and remove octant index everywhere. So this is quadrant index. And yeah, this is just the lookup into the walk table based on the quadrant index. So I believe that should be a fairly straightforward change, but I don't actually know. So let's take a look. It looks like we did still have some people passing a remainder z call here. So that actually makes sense, though, because we didn't neuter this call's z test, right? So when we are calling this code to get us the quadrant index, that actually does make a fair bit of sense there, because we need to remove the z from our request in get quadrant 4, because we're passing 1 here, right? So the remainder value is producing an accurate estimate of where we are in z, and we don't want to do that, right? That's actually correct. Like, that assertion was telling us something valid, right? Okay. So I think that should be computing the quadrant table properly. But I also don't know where we allocate those tables. If it actually needs to be doing, like, when we're doing this max dest count here, the max cost per ray is, so you know what? It's already factored in. So we're already not going to push more space on, because we have the y and the x are now the only two things that we iterate over to produce the table, so it won't ever allocate ones for z. So this stepping is now, I think, computed correctly in that sense, right? Like it's now, that's now okay. Like, I think that's actually fine. So when we go to do grid build spatial partition here, this part we have to take a look at as well, because I hope now that all of the things are still getting inserted into the spatial partition, but I guess we don't actually know whether that's true or not. So hard to say, but I think we are now properly walking through only 2D, and we're properly aligning, if that green box is correct, the spatial partition. So I think we're probably okay. That said, the initial lookup into where we would be in the spatial partition is probably, well, I don't know, it might be wrong. This code right here, where we do initial grid index, and we get a flat index from the half atlas index plus the atlas spatial grid index offset. Because that atlas to spatial grid index offset now has a 0 z value, in theory, we should always be addressing with a 0 z value into the spatial partition. But I would like to take a quick moment to see if I'm right about that. Because again, like, it's important that we never now ever use z in that way. So if we look at the atlas to spatial, you can see the z value is 0 there. The half atlas index is all zeros. So the z value that we would be looking at would also be 0. So is that true like most of the time? Hopefully. I'm just taking a look at what this half atlas index z value is, right? But it looks like there, it's always pegged to 0 for all intents and purposes, right? All right. So I guess now that we're probably only stepping in 2 dimensions, now would probably be a good time to debug some of the lighting stuff that we are seeing. So let's try to do an inspection of the spatial partition somehow. Maybe we just insert some new code to draw it, since it doesn't look like we really had much code to draw it. So maybe we, the octahedral, because we're in a failure state right now where there's no lighting being generated, so I should be able to safely turn off the directional drawing, because we don't need to know that. Like, we can see that the lighting is being computed incorrectly just by the fact that there's no lighting. So I can turn off the probe directions in the octahedral, the debug draw octahedral values. So we'll start there. And we'll say, yeah, don't draw those directional values. The debug draw color dir, this thing. Let's just not. We just aren't going to do that. So now we'll only be drawing just the boxes, because I would like to see where they are, right? So I would like that. Maybe, because there's less, I can also draw the actual atlas. Because it's not drawing the little lines anymore. So now we can see, like, that's the complete set of light probe locations. So that's good. I will turn off the colliders for now, because we don't really need them. They're just adding visual noise. Because we know that they're roughly exactly where the things we see on the screen are, and they just extend up higher if they are walls. That's about it, right? So, here's just the general thing we're looking at. And now let's try, if we can, to draw the spatial partition in some way. So if I go ahead and do something like debug draw spatial grid or something like that. We wouldn't be taking any atlases because these are just, this is its own, like David S. Pumpkins, it's its own thing. So we should be able to go ahead and take the spatial grid and step over the actual voxel. So we know we're going to have, you know, just X and Y here for the spatial grid, right? We're basically going to have something that looks like this. And the voxel grid itself, I can kind of pull out as spatial grid like so. And we can loop over the actual dimensions of the spatial grid here. So we've got the cell count X and Y, and we can also assert that the spatial grid cell count Z equals 1, right? Now in here, I mean, the first thing we can do is just see what the actual grid locations are, because we should be able to do that by just calling get cell bounds, right? So if I want to, I can say, like, look, just where is this thing? Like where is the spatial grid of this thing? And we'll start there. So if I said get cell bounds and I said it's, you know, X, Y, 0, what would you claim that looks like, right? And I'm gonna have to put a color in here. So since we're using green, it's green for now. And if I call this right after the octahedral values, I should be able to, yeah, figure out what that looks like. Little parentheses nonsense there. So push debug box gets cell bounds, and then the color value is a v3, not a v. Oops, a v3, not a v3s. What is debug push box complaining about? Solution get cell bounds. That's a rectangle 3, which is what we want. Oh, it's a v4. I'm sorry. It takes alpha as well. Whoa, isn't that fancy? Okay. Calling the code now. We should see the actual voxel, right? Which in this case is you know, just tall, thin boxes. That's exactly what I would expect. There should be no vertical dividers, right? Because there's only one layer. So there's our, you know, our voxel. Now I'm gonna do a little bit of like a color variation here. Now because I don't care about. Well, actually, you know what though? Let me ask one quick question. Were there 8, I guess, light locations here? It does look like it. So I do think it's correct in that there are 8 per cell, which I think is the correct number, right? So that looks like it aligns the way I would expect. That looks fine. I think that's fine. Right? I think that's okay. But you know, we'll look a little closer later. All right. So I'm gonna. Why is the compilation? There we go. I'm gonna do one other thing here with the coloring, just so we can see it a little bit better. I'm going to maybe like alternate between 2 different colors. So like maybe we do something like I don't know, X. This is just, who knows, right? Something like this nonsense. So I'm just gonna make like some kind of a way of making neighboring cells use like a different color. You know what I mean? So maybe like some cells are yellow and some cells are magenta, or some cells cyan. I don't know, something like that. Maybe cyan and magenta. Let's do cyan and magenta. So that we can sort of alternate between them in some way that, you know, allows us to see the different cells more cleanly. Now, the problem is they're going to kind of overwrite each other because they abut. But you can kind of see, you know, that there's like, now there's like a checkerboard pattern, you know, right? Of these things. And so if I shrink them slightly, so let's say we do a bounds here where we say shrink this ever so slightly. So, you know, just a little bit, so that I can see these, just so I can make sure that my checkerboard is correct. What is the complaint? That's the complaint. Probably safe to start using auto now these days, right? Can we do this now? Yeah. So, you know, we could start using auto sometime on Handmade Hero if we wanted to. I don't know if we want to. It's really not that necessary, but, you know, saves you a little time. All right. So in theory, now if we look, we should be able to see sort of a checkerboard pattern there, right? And you can kind of see it. There's like a checkerboard pattern of magenta and cyan. And, you know, the only reason I'm doing that is because if we get rid now of the, when I said shrink, I meant shrink. For some reason, instead of shrinking, I enlarged. Oops. Don't you hate it when you enlarge instead of shrink? With this one weird trick. Anyway, you can look and see the checkerboard pattern, which I just wanted now so that if I go draw the things that are supposedly in these spatial partitions, I would be able to see sort of like which spatial partition they were in by their color, at least a little bit. So let's go ahead and take a look at how we pull things out of the spatial grid now. So if you look at the lighting code here, you can see that we've got these like nodes and leaves. You know, I think the nodes literally just say how many leaves there are, right? That's it. And I do think that, like, you know, in the future, we can probably get rid of that indirection entirely because we know that the geometry is relatively simple. We could probably just say that there's 4 boxes or 8 boxes per cell, and that's the end of it. And that would also simplify the code quite a bit. So yeah. Anyway. So if we look at this code, if we get out the spatial node from, I'm assuming that we can simply make a call to get that, right? Where we can ask for the flat index and grab out the node directly from there, right? So, you know, this kind of thing. So in theory, we should be able to say like, hey, get us whatever the flat index is for the particular node that we're talking about, which in this case we already have. It's this. So if we want to do a flat index from the node index here, in theory we just pass the spatial grid and it should just do it, right? So that should pull the node out, and after we have the node, we should be able to do just the simple leaf loop here, which gets us all of the leaves. And so then really all we have to do is look at the leaf and draw it, right? So if we look at one of these grid leaf structures, you can see we've got a boxmin and a boxmax. We can just pull out all 4 of them and draw them one at a time. I don't actually remember what we defined our V3, so it just looks like this, right? So we can literally just like go through all 4 of them like with a for I loop, right? You can just say, hey, let's loop over those. In fact, we could even do this. Loop over the boxmin maybe like this, x dot e, right? So however many there are, that's how many we're going to loop over. And then we can literally draw what the boxes are supposedly in this thing. So we would know that the box is like, you know, the bounds for this thing are erect min max that's going to come from slicing off of this, you know, V3, this sort of SIMD wide V3 value. I wish the cats have definitely decided that they don't love my microphone. They're not fans of it. So they keep knocking the cord down, which is always good. Let's put that back up. So we just need to grab out the, you know, the X, Y, and the Z of a particular slice, which is pretty easy to do. We may actually have extraction routines for that. I don't actually remember, but I'll take a quick look because we may have a way of you just grabbing out a slice because it's something you want to do when you're debugging. Yeah, you can see it right here. So we can just use get component to do it. And that should be pretty straightforward. So we want to take the boxmin and the boxmax, and again we're just slicing this array to grab out the SIMD portion, you know, into a scalar portion to use debug routines on it. That's it. I guess I'll do box bounds here just to disambiguate it so that it doesn't use the same value as this. This is the cell bounds, so we'll call it cell bounds and box bounds so that we're clear on which bounds are which. And now I just want to look and see, like, what are we looking at? Like, what's in the spatial partition, right? And so I'm going to start by turning off the cell boundaries so that I just am only looking at leaves here. And then we're going to just debug the spatial building code till we see correct stuff, right? So right off the bat, you can kind of see the problem. Some debug system nonsense there. It looks like we're really not putting anything in here. You know what I'm saying? So it looks like we're getting an early failure when we're trying to build the spatial partition. We've got some error probably with the way that we're handling our Z, right? Where we're thinking that nothing is actually included in the region. So I would assume that this is a simple case of, again, just not like treating these values like, because we didn't quite produce the values to be completely correct here. So when we did the zeroing out the z, so if we take a look at the grid build, grid build, there it is. So we take a look at grid build spatial partition here, and we look at what we're passing in. We start by talking about a thing called a clipping region, which starts with the total bounds, which is what we'd expect. We then reduce the total bounds by one cell, and there's your answer right there. So that would completely eliminate our z. So we don't want to do that, right? So we want to do a clip shrink here that looks like that, and we want to get rid of the z. So this way, we're keeping the full range. That obviously was a huge issue, so that's, we had to fix that, but we're probably not quite done yet. So for starters, we need to prevent that shrinking of the clipping volume, and it looks like somehow that didn't change anything, which is odd, but oh well. And then when we go through here and we walk through all the boxes that are in the lighting solution, you can see us sort of looking at, we're getting indexes for those mins and maxes in the spatial grid, right? And then we're looping over them and figuring out like where they will reside. So that looks fine. Like, I will have to step through it and see if I may be missing something, but that looks fine. Then we go through here. We do clipping to the clipping region, which should not really be a problem. This should all just be 0. Let me assert that z equals 0 here. Because, like, we never really want anything else. But yeah. The cell bounds that come out of this, we viewed those and they were right, so that should be okay. So yeah, I'm not really seeing what's screwed up about this routine, but obviously something pretty basic is. So this is our problem, right? So we set the apron on Z, and we never want that, right? So the apron for terminating the grid walk we never ever want that to count Z as part of the apron. So I don't know if that really has much to do with it here, but that was certainly a problem. So that would have cleared out anything in the spatial partition at that point. So let's take a quick look here. We gotta we're pushing a few too many things down. So let's take a quick look at turning this off. We need better debug diagramming support. I think we added reasonable new ones, but this lighting system uses its own, which is kind of stupid. Unifying those would be nice, right? All right, so here's our, supposed spatial elements, for lack of a better term. And I'll be honest, they don't look convincing to me. There's a lot of kind of gunk in there, and I'm not sure I totally understand why. You know what I'm saying to you? So what's going on? Amusingly, the lighting now works again. So it was that the fact that it was setting the entire grid to the termination apron, because it happened to be on the edge in Z, which was true. We just don't ever allow you to go off the edge in Z anymore, so that's not an issue. There's something weird about these boxes, right? Like I don't really understand what I'm seeing. They're really kind of incoherent with respect, like they're very sort of like oddly aligned in weird ways. So it feels a little off, like either I'm drawing them wrong or something. At the same time, they do seem accurately placed, like around, like, say, the heroes. There's the light. I believe that is the light that's hanging above the hero's head, or something, or the hero's collision volume or whatever. Is not actually that inaccurate. It's following the hero correctly and stuff. So it's a little confusing to me because it doesn't look that off. So I am having a little bit of a hard time parsing what I'm seeing because it's a little confusing. But at the same time, like what the heck is that? Right? And amusingly, those boxes there, which seem to coincide with light sources, like that's where the light sources are as well. Those seem to be the places where we were getting the weird non-lit probes as well. So I feel like there's just some basic stupidity going on here in a couple different ways. So we kind of need, we can see like that's a light. Where the lights are, we get these extra overlays. And we probably need to fix that. In fact, this may have been a bug that's been in here for a while. The thing that says whether you're inside something or not may have incorrectly said don't probe if you're inside a light, which is wrong. Because lights are not supposed to be occluders. You know what I'm saying? So that's a tough one. That's a tough one. How we're supposed to handle that, I'm not sure. Maybe the way you handle that is like, so when you hit something, you gather from the light probe in that area, right? And so the way that the actual lighting function works, where you do the casting, right? You do the grid raycast, this thing. The transmission level is gathered from, hold on a second. Emission, there we go. Hit emission. So you can see this like is emission value here that allows light sources to inject light into the system. And so really this like any true this thing, really what should probably happen there is we should have written out the emission value. If you're inside a light source, then your emission should be the light source value, right? So that's confusing. So I don't really know, like, so really I think that's not it's not appropriate. Like, that doesn't make a lot of sense. You presumably want this thing to properly set the emission value here or something, right? Like, that's just kind of, it's obviously garbage. So we probably want that to be fixed, right? All right. So so that's busted, but that's not really the problem that concerns me at the immediate moment. Right. Problem that concerns me at the immediate moment is why this looks like such a tangled mess. I guess part of it is that there are ceilings, right? Like there is a ceiling here. These things. So there is that, and then I don't know about some of these side things here. It's a little hard to say what we're actually looking at. One thing I do think is really weird is I don't understand why these lights are so big. I guess one reason the lights are big is to make them easier to hit or something, but it's a bit odd, right? It is a bit odd. But, you know, looking at it, I don't know. It's at least, we did figure out what the primary bug was there, I think, which is the fact that it was setting the terminating apron to the wrong thing. So that's a start, but we're still a little bit far from good here. So let me take a quick look. Let's get rid of debug draw spatial grid, the call here, and let's just look again at what we're actually looking at now in terms of, you know, the look of the world. So it's like not fabulous, but it's like it's just off. It's like, you know, you can tell that it's still a bit buggy, but we've eliminated the really egregious error, right? And frame rate wise, we're excellent. If we look at our frame rate here, we're totally rocking 60 frames a second just fine now. And I think we could crank up the lighting quite a bit now. So yeah, I think we're okay. So really we're now looking more at figuring out what's going on with the light transport. The shift to off center has clearly kind of made it screwed up a bit. And so figuring out what's going on there, I think, is our next goal. Increasing the light shading rate would be good too. And that's kind of a separate issue. So let's look at that light shading rate issue. So the light shading rate issue is we would like this to look more like, say, that. Which is probably a bit aggressive. So, you know, maybe probably won't be able to get it that good. But if you take a look at what happens when we increase the shade, the response rate, you can see how noisy, how much error there is because there's just very little smoothing going on. And again, that's just because it's a stochastically sampled thing, and we're also not sampling it particularly brilliantly. Like, we don't necessarily, you know, we're not horrible with how we're sampling lighting, but we're not great. And so you can see it's better or worse at certain times. Like, you know, it's actually not that bad there. There's only a little bit of flicker. But in order to improve the quality of this, what we want to do is cast like more rays so that we can reduce the degree of lag. So if we go down to basically like, if we're going at 60 frames a second and we use a quarter, right? So it'd be 4 of those 60ths of a second, right? That would be a pretty reasonable response rate, and we'd only have to cast about, you know, I don't know what the threshold would be here. So maybe 7 times more rays, maybe 4 times more rays. Let's look at 4 over 60 here, or 5 over 60. How bad is 5 over 60? I don't really know. So response rate wise, so the quality of 5 over 60 isn't perfect, but it's pretty good. So I would kind of say, like, at 5 over 60, I think we'd be okay, quality-wise. So that's 4 times as many rays, which I think we can do. Like, I think that's plausible, right? What is going on here, by the way? Why is our apron code, like, somehow missing? We changed the Z, and, like, our apron code doesn't generate an apron on the right border. On the positive border side for some reason, right? More stuff as we go simplify. We'll have to, like, make that work a lot better. Anyways, so yeah, I wonder if that's a good place to call it for today. But yeah, looking at the difference here, a difference between of casting maybe 4 times as many rays isn't like that bad, right? And if we cast 4 times as many rays, we would have that quality while still being as responsive as a 20 over 60, which is pretty responsive. Like, that's pretty fast, right? So we'd have reasonable quality at fairly high responsive. That's pretty darn close. I don't think anyone would notice, like, that as being laggy. So I think we can get to roughly this speed, which would be great. And that's because, and we might even be able to do better than that because things will be much simpler now, we can optimize that raycasting routine more than we did before, because we might be able to do things to, like, we might be able to make some clever optimizations now knowing that Z is off the table, which we previously couldn't really do. So yeah, so I think that's all right, but again, gonna have to do some work to get there. So one of the ways that this thing currently works, if you look at how the grid raycast goes, so here's the grid raycaster, right? The way this works is it takes a ray origin and it does a cast of that ray through the environment using, it's a wide cast in the sense that it compares against multiple things in the environment. The rays themselves are not wide. It casts a single ray for this walk, right? And then when it's done, doing the walk, it does the sample to pull out of the voxel, right, what the lighting is there. And then it writes that into the spec texel at that location. Right. Now, to be honest, I don't really remember why this is as wide as it is. So if you look at what it's doing here, it's blending with... It's blending with 5 times 4. I'm sorry, 6 times 4. So 24. 24 floats, which is all 8 octahedral locations. But I don't quite know why that would be happening. I see. So in a single step of this routine, we actually do 8 raycasts, one out of each direction of the octahedral. So then now I do. Okay. So we cast 8 rays at a time, not wide, just we do a loop over 8 rays and then we blend them back in one step, which makes good sense. I mean, sure. So that all seems fine. And it seems to me like we could run the grid raycast more times. So you would think that that would mean that basically like this routine, we could just run it multiple times, right? So and to be honest, probably you'd get more efficiency by welding that into grid raycast, where grid raycast itself actually did it, because then you wouldn't do the load modify right multiple times for no reason. So it'd be more efficient if grid raycast could have built into it the idea that the sample direction could be updated inside that loop. So it would just do that loop like a few times, right? So I do think this is a little inefficient if we updated it the way that I'm suggesting. But that said, so if we look here at the way that the light sampling is going, you can see here that's like entropy index, and it's, you know, it's got sort of a way of looping through to pull out which directions the rays are getting sampled in, right? And presumably we base that off of presumably we base that off of some kind of, what is entropy frame count used for, by the way? Absolutely nothing. All right. So like the sample point entropy and the light point entropy are the two things that are updated, I believe. Let's take a look. Light point entropy. Is this ever used? So light point entropy is not used because we don't sample light sources specifically anymore, right? All right. So really it's just sample point entropy. That gets sort of walked randomly as it goes. And the entropy index here gets added every time after the full cast gets called. I mean, these are all pre-computed lookups into a table anyway, so I'm not quite sure that this makes a ton of sense, how we're doing this here. like, do we actually care about entropy in that way? I can't imagine we actually do. Like, I would be surprised if we saw a huge difference in the way that stuff works, right? It seems unlikely. So I don't really know about that. I also think that the way that this is set up here doesn't make a whole lot of sense either. Also, this doesn't need a loop over z because z can't ever be anything anyway, so it's only ever going to be a loop over x because the atlas can only do 2. Well, that's not true. I guess we have to do 2 layers of it, so that's not entirely true. So I would say this entropy index value probably doesn't want to be updated here. That seems unlikely. Probably what wants to happen is something like this. So inside full cast, it can update the entropy based on how many times it does this. So maybe this is a pointer. And so in here, it would be more like, okay, star entropy index, and that's how the entropy index comes out of this thing. And then we do an entropy index plus in here or something, right? I don't think this is great. Like, I think we'll probably want to change the way it's doing, but I'm just kind of see what happens if we hack this in. So that should be the same now as it was. Yeah. But we should now, in theory, be able to, like, loop this. So, in other words, if we want to, in this piece of code here, we should be able to do something like do multiple samples. So, there's like a sample batch, and we just say, all right, there's going to be like 8 sample batches run every frame, or something like this, which will slow things down a lot, but I just want to see if it works. Yeah. So oddly enough, the smoothing is not as much as it should be really there. So I think this is still a little bit busted. So I'm just going to play with this value and see what happens. Yeah, so I think I'm like thinking of this wrong or something, because that weirdly doesn't seem to change what's happening. And weirder still, like it doesn't have as much of an effect on the frame rate as it should. I guess it kind of does. I mean, that's significantly more than it was. But this is 16 times the amount of rays, so that's a lot. So in theory, it should have been able to produce sort of an equivalent. So I guess maybe part of the problem is because it's just taking more samples of the same world state. It doesn't diffuse as many times as it should, meaning this this Atlas like update doesn't run. So it could be that kind of has a lot to do with it, right? Like the casting the more rays doesn't really help if those casts aren't then fed back through the system. Maybe. I'm not really sure. So that's a tough, I don't know. That's very strange. Makes me think maybe we've got some buggy assumptions somewhere else, maybe, that's making the lighting flicker more than it should, right? That's kind of my hunch there, right? So I don't know about that. That's a little, yeah. Because the lighting values that are actually getting interpolated would in theory be a lot more stable now. However, it is true that if they don't write back to the diffuse texture, then maybe that lack of convecting the value around does make a difference. I don't know. That's a tough one. That is a tough one. So I guess I would say, well, what happens if you run this thing multiple times, which would be much more expensive. So this will slow down the frame rate like pretty viciously, right? But I'm just curious to see if that is what would happen then. So if we did a for sample batch here, right? And we just ran this thing multiple times, then what happens? So something seems up, because that should then spread the values out multiple times. It should be the exact same lighting as the one that we were doing before, right? So I guess, well, do I have to change the blend rate though? I mean, maybe I have to change the blend rate. That's, I guess, another question. Right, so the update rate maybe has to be set down again to something small, right? So yeah, I'm not really sure what to make of that. I think we probably want to just go hunting for bugs. I think we're really seeing like other things now. But man, the amount of performance we get back is kind of sick, because like I'm just throwing in times 16 to the times 32, and the thing still runs at like 30 frames a second. So yeah, I guess the answer really is don't throw out the lighting code, because it looks like we can rescue this. It looks pretty good. So yeah, I think it just needs a little bit of meticulous care here to re-clean it up. But you know, yeah, I mean, there's some weird stuff going on that I think we can fix. But there's it updating basically like locked, like it's very, very like almost no perceivable lag, and it's perfectly smooth. So really, there's just this weird, like, there's some weird stuff happening where when the voxels shift, that like as we move. So I think there's just other bugs here. So if we just go actually take care of this, I think we're in good shape. I think we're gonna get our fully dynamic global illumination and just have our cake and eat it too. So maybe I'll stop for today. It's been about 3.5 hours. That's a pretty long time to go without a break. So I guess, yeah. I mean, I am relatively optimistic about that. Like that just seems pretty promising. So I think we might just be able to just have this thing work, and it's going to be okay, which is kind of nuts. But I think that might be okay. So I think we just have to go through now and be a little bit more meticulous about removing Z. You know what I'm saying? Because it's pretty clear that our spatial partition is messed up, and because the way that the lighting system works is it's very specific as well about making sure that it aligns the atlases and the spatial grid together, and I don't actually know if that's like currently still working properly either with the way that the walk table is computed. You know what I'm saying? Like you can see here the starting location having being based on some ideas about where stuff is in the world relative. Like this starting location bakes in knowledge of how the atlas is centered relative to the spatial grid, you know? And so I'm not sure whether that stuff's correct either. I think it looks like it roughly is, because they did look like they were aligned in exactly this way. And we now don't care about the z value, right? Because the z value doesn't matter. So I do think we're roughly correct, but again, you could see that there was just, there were definitely some bugs in there. So my assumption now is just that, like, yeah, I'm going to have to kind of fine-tooth comb it, but I think we can use this. I think it's actually pretty good. So maybe we're just kind of done with lighting it rather than having to simplify it. What we have may just be good enough, and so let's just debug the 2Di'd version of it, and then we can just have it, and that'll be nice, because that just takes a huge thing off the table for us. So that's pretty good. That's pretty good. I would say, like, also 32 oops, 166 is surely not going to be good. 16 might be more what we can afford. I mean, obviously we might get some more optimizations out of this, but in terms of like looking at what's feasible to do at 16 frames, 16 milliseconds a frame, this is closer to it. So I think I would be more comfortable saying this can hit 60 than 32. So I think we might try to see, like, can we make sure the lighting is stable at 16, and go from there, right? So we'll see. We'll see. All right. Maybe that's good enough for today. And next time what we'll do is we'll try to pick up where we left off here and take a look at what can we reasonably do to clean up the spatial partition, make sure we're actually intersecting rays properly, probably put the debug, we have debug code that draws ray intersections, look at those more carefully, make sure they look plausible, so we can kind of get rid of obvious errors in the system there. So that's probably all we really need to do. Yeah. So I think that's all good. All right, folks. So I think I'm going to wrap it up. I'm going to wrap that up for today. Thanks, everyone, for joining me. And we will do another stream soon where we take a look at just debugging that spatial partition and trying to get that walk straightened out. So thanks, everybody. And soon before next Sunday, possibly, yeah. I might stream more frequently, yeah. So thanks, everybody. And I will be back to take a look at that code sometime soon. Take it easy, everybody.